Yeah.
Oh yeah, I could have stood on that. Thanks. Okay, yeah, in general you can mix and match, no problem. In fact, it's a highly recommended way to go. And even there, where you saw in some of the previous graphics, where we're dropping in blocks around the HLS, in many cases those are highly optimized blocks. So I mean, for example, you don't craft a memory controller in HLS. You know, it's not what it's used for. Okay. So moving to PYNQ then, and quick check. How many of you are Jupyter Notebook aware or familiar? Or okay, so that's good. And how many of you use Jupyter Notebooks? Okay, very good. So this is a recent phenomenon, and I say phenomenon in the true sense. And essentially, it's using a web browser in a new way. All the things that you were familiar with, all the rich multimedia are in there, but now you have code that can execute and produce its results as well in the web browser. And this started off as IPython notebooks. It became so popular in the computing community that they broadened it to Jupyter notebooks, Jupyter standing for Julia, Python, and R. And the key to that is that the architecture here is essentially a web server. So you have a kernel that is exposed through a Tornado web server via 0MQ, which was mentioned earlier, and then that serves up this interface. And because it was so well architected and because it's so open and well defined, many other groups came along and said, like this a lot, but want to do it with something other than Python. So they put in Jupyter, they put in R. Most recently, the CERN guys have put in C++. So if you've never seen interactive C++ before, you can do that in a Jupyter notebook these days, which I thought was a contradiction in terms, given what I knew about Jupyter. But so this has taken off. I mean, to say that this has captured the imagination of a community is an understatement. Every major company is using this today. Amazon uses it to front end all their SageMaker, AI tools, etc. on the cloud. This 2017 software award, an award at some level, except that this was won by Unix, by TCP/IP, by Eclipse, by Java. And if you get this award from the software folks, I think you're doing well. So this is probably more like the Nobel Prize of software, albeit it's not the ACM Turing Award, but we'll get to that later. And this is actually adoption and projected adoption, and is available as a Jupyter notebook, so you can run it and verify the things, etc. One of the keys here, if you read the original, now there's an incredibly strong reason why this is good. It was designed by two physicists, so you know it's good. One is Fernando Perez, who's currently at Berkeley, but they were at Colorado at the time, and the other is Brian Granger, who's currently in the physics department at Cal Poly. So what I really like about this was they were responding to the problems they saw and designing solutions to the problems they had. If you look at the grant letter that they originally wrote, they emphasized very heavily reproducible science. In their words, a modern paper can sometimes be little more than a marketing brochure. You read the paper, you cannot recreate the work, you cannot even get close to recreating the work, and that's really frustrating and really annoying. So one of the drivers behind notebooks was I should be able to give you something which would allow you to run what I ran, and then allow you to change it and say, yeah, that's cool. You know, for those assumptions, I'm good, but what I really want to try is something else. I want to see how it works under these conditions. And another physics reference, when the LIGO guys, is it LIGO or LIGO? LIGO, okay, sorry. When the LIGO guys established their proof of the distortion of the the distortion of field proving Einstein's predictions, they published their results as Jupyter notebooks so that other physicists could actually run through the calculations, download them, run through the calculations, and verify that their procedure was correct. So I think there's a huge value proposition here, and it doesn't restrict itself to science. We have the same kinds of challenges in advanced engineering. When you're trying to build systems, when you're trying to leave a legacy for other people to use. I think I heard documentation mentioned twice in the two talks this morning saying, you know, and we will have good documentation soon, and we're trying to get somebody to write it. This goes a long way to doing that in the first instance. So we saw this and we were impressed and thought this is a trend that, and of course it's all open source and extremely well architected. One piece of feedback that they got was, notebooks are cool, but I really need an IDE. I need code editors, I need terminals, I need file browsers, I need all the other things I need as an IDE. So they came up with a a JavaScript library called Phosphor.js, which was done by Continuum Analytics, the guys who do Anaconda, and this allowed them to have multiple windows in a single browser. Now, this was important, and that then allowed them to build an environment which is essentially a browser-based IDE. And this is completely extensible. So all of this can be, in fact, it's encouraged to make it extensible. Now, why we like that in particular in research is because some of you will say, and we get this, fairly regularly, but your tools don't run on Macs. And you're absolutely right. And you know what it's like, OS X, Windows 7, Windows 10, GNU, Unity, what windowing system do you want to work on? This is the new windowing system I'm predicting for a majority of tools. This is an environment which is totally standardized, totally open, supported by all browsers, and is one of the most sought after and competitive environments in the sense that several manufacturers are pushing the edge here all the time. So we thought this was very impressive and wondered about how we could use it and how we could leverage it in FPGA land. The other thing we saw at the same time, and this was us looking to open source, if you will, for inspiration, was the complete, rise of dynamic programming languages in general, but Python in particular. And that was mentioned this morning fairly strongly. And it really is a quite dramatic growth, as you can see here. What also caught our eye was that, in particular, with respect to Python, that it's emerging for the first time as a language that's used in embedded systems. So this little icon with the chip here is meant to mean a language that's used for embedded systems. The others are World Wide Web programming, mobile, and server desktop. And even IEEE was commenting on this, and to some extent the Raspberry Pi brought this phenomenon in. And there are two things happening there. The first is you're seeing Python in embedded programmings, and it's also getting rid of cross-compilation. Now, I've tried this out with my computer science colleagues, the professors I know and talk to regularly, and we've concluded that embedded systems engineers, particularly embedded software engineers, are like the analog engineers of the computer science community. They're increasingly this, relatively speaking, smaller group as a proportion of the whole, and their craft is seen as a highly specialized, highly, let the analog guys do what they do, and we'll build the rest of the system. So it's interesting that languages like Python might enter into this embedded space because it would potentially accelerate. If you can dissociate the hardware-aware software from the application stack, the rest of the application stack, and if that can be written in languages other than today's embedded languages, that could be very powerful. And the other learning here is that it's not a question of Python or C++, and this point was made very well in a couple of this morning's talks. If you need the C or C++, you write it in that, and then you wrap it in Python, and you go from there. So what does this bring you? Well, during development, not everybody is a cross-compilation C++ expert. If you can give them a platform with Python interfaces that they can use to develop, that's very powerful. If post-deployment you actually have a scripting language built into your platform so that you can actually do other experiments and your customer can extend it, that's very powerful. And then the next thing that we coupled that to was saying, well, why don't we take the two of these ideas and join them? So in our case, we have this legacy of coming from hardware engineering, embedded software. We're facing many, many new users who are not from that background. And so this PYNQ project that we had, which was Python productivity on Zinc, now it also uses Jupyter, but if I'd called it Jupyter productivity on Zinc, it would have come out as junk, as against PYNQ, so you can kind of see where we were going. And really we had two goals here. One was to make it easier for more people to actually experience the platform, and I'll show you a live example of this. And then also make it easier for people who are creating good platforms to get them into the hands of the end users who don't necessarily have all the skills of the creators. So let's say you did a fantastic correlator design or some other design, and you need to get it in the hands of a physicist who has no idea what an FPGA is. What hope would there be for that, and how would you do it? So what we did was we took the Jupyter stack and we put it on the A53s of the Zinc and Zinc UltraScale parts. We've run this on the ARM A9s as well, and it's perfectly performant. So we put on a standard Ubuntu here. This is the IPython kernel. It could be any other kernel. And this is the Jupyter Web Server, the Tornado client with the 0MQ stuff. And now this web serves to arbitrary platforms externally, and we have it running on the Zinc devices. Another really cool feature of this is that now we can have lots of clever visualizations and interfaces because they're all being rendered by the graphics cards in the clients. So the target doesn't have to do that because it's a web server. You can do lots of nice visualizations, and we'll show you some, but they're actually being done by the client rather than the embedded system, which is very productive again. And today, JavaScript and TypeScript probably has the best environment for data visualization. That's thanks to D3 from Stanford and various other libraries that you'll come across. So that was part of the problem, if you will, getting the processor side of things going. But then we wanted to expose the benefits of putting accelerators and other logic into the FPGA. So this is our Zinc UltraScale fabric. And we have this idea of overlays or user designs, which are then wrapped in C, C++, and exposed as Python libraries. Now, what we're thinking of there is really a design pattern. You identify something that's repeatedly useful, that you've seen a number of times. You design an instance of that can solve the problem for a number of different users, and then you wrap that so it's available as a library in the same way that Python libraries do this all the time. So rather than, I guess one example of this would be if I had an FPGA controlling a drone, I might design that circuit specifically for that drone. But if I had done that 2 or 3 or 4 times and each one was marginally different, I might try to design a design which could be generic in the sense that it could control 4 or 5 different drones, and I'd give it a software API and then I could customize it. So that's the way we're thinking here. And so we wrap that in our C API and we create a Python package for that, and then we import that along with other libraries. And so this is what we've been doing with PYNQ. It's a way of delivering hardware functionality along with software functionality from the experts who know how to do the hardware to the broader community of software folk who may not. One nice thing about Jupyter notebooks is that they render on GitHub. So these are examples of Jupyter notebooks for hardware-software co-designs. This is a neural network, quantized neural network. This is a Park-Clark motor control example. If that was perfectly circular, the fields would be being excited correctly. This is one I'll show a little bit more in detail. Here we have a resizer IP in the fabric. This is the ARM device. This is a DRAM. This is a DMA. And we're offloading the resizing of images to hardware accelerated. And this one's an OpenCV example. Now, if this was Python, and I saw something like this on PyPy, the package index, I could pip install it, and that would be cool, right? So we thought, well, wonder if you could do that. And so in this case, for this example, we've now extended the packaging to include the FPGA components. That means the bit stream plus the C drivers plus the Python APIs, so that with a single pip install command, you can now actually take that notebook, that design, onto your board and run it. So this is the kind of ease of use that we're exploring as a way to make it easier for people to reproduce the work of others. So we have some of these designs that you can see on the web today and actually download onto various boards and use them. What happens when you do that? You download it to your board, and we'll say this is a Zinc device, and so you have an ARM processor subsystem on the left, and then you have your FPGA on the right, and some interfaces between the two. Then what we do is we instantiate from our PYNQ library, we import our overlay class. We instantiate an object of type overlay with the parameterization to the bit stream that we've just downloaded from GitHub. And effectively that loads the device, and it also loads the software stack that's with it. And we do further tricks to enhance the user experience. So for example, we bring down not just the bit stream, we package that, but we package the metadata. Now that can be the tickle file or the HWH file, or there's now an XCL bin file, there's another format coming. And from that we can extract the metadata of the design. And again, I think Jay said this morning about how metadata can be very valuable and how you can add user experience, enhance the user experience with metadata. So what we do is we create a Python dictionary from the design metadata, and with that we can effectively do additional things. So for example, we can set the clocks in the processor subsystem to be correct for the design that's come down. If we find this design does not have a device driver for it, for example, in the kernel space, we can assign it temporarily an MMIO driver so that now you can at least from Python peek and poke to that and script something and check that if it works. So here, if somebody brought this, if a hardware person, for example, brought this in and they hadn't had time to get their software guy to write the kernel driver for them, they would actually in Python be able to interact with this, verify the hardware design, send the setup register packets or fields, etc., read things back, and then by the time the software guy came back, they'd say, yeah, I've been through it 2 or 3 times, I now know what the interface should look like, and here's the working version that you can now go and write me a driver for, if that's what the ultimate goal is. So we feel that there's a lot of potential here. This is an example of the notebooks from the resizer design. So this is very simply an image which we just display in the notebook being resized using the Python pill library, and that's running on the Arm processor. This is the change to run the same code but accelerated in the design we showed you earlier with the DMA out to the resizer IP in the fabric and then DMA back into the DRAM, etc. So we've actually also used the whole buffer protocol, the ND array idea. Python guys did a lot of, the guys who did NumPy were very, very clever at multiple levels. I mean, apart from exposing C-type data structures into Python, they also made it very efficiently to go across that backwards and forwards between the 2 languages. And we exploit that really strongly here. So here you can have an extremely well-documented example of a design. You can do things in software or hardware, and we think this brings new thresholds as to what's possible. So PYNQ then is an open source framework. The parts in PYNQ are meant to be the parts that we contributed. So we have some examples of PYNQ IPs. I won't go into too many of those. We have some example overlays. You can use user designs as well. We enable all of the, out of the box, we enable all of the Linux drivers that you might like or need to use. And we also then wrap those in Python APIs. And we have notebooks showing how these work and workshops, etc. And then once you get into this space, when you have this environment, then all the massive ecosystem of Python becomes available to you. And now you can do like Pillow, for example, or Pill. Once you're in Python land, you get that. And it's extremely valuable. So you saw this board earlier on. I'm going to bring this back to the RF SoC. This is the eval board for the RF SoC device that Luke was talking about. We did an example on this board, which is a very simple radio, possibly one of the simplest you could do, and certainly not doing justice to the hardware on the board, but it's a QPSK radio as a demo. And we were using this demo because we wanted to show how this might work in PYNQ. And then we ran everything on the RF SoC itself. So this is what we've got. We've got our symbol generation, the pulse shaping, interpolation filters, our up converters into our RF DAC, loopback into the receiver side. This is at 1 gigahertz, so it's a real signal. Back into the ADC, down conversion, etc. Decimation filters, match filter, and outcome are symbols for QPSK. And the whole thing is being orchestrated by the A53s on the platform. So if this works, I should be able to show you what it looks like. So this is a demo I did earlier this year live in front of our CEO. So it has been verified and is not slideware. And what I will attempt to do is show you what this looks like and what we can do in Jupyter Notebooks on RF SoC. The context for this demo is it's a result of a collaboration with our partners at the University of Strathclyde. It's based on the open source PYNQ framework, which is running on the RF SoC. We're randomly generating some data in the baseband at 1 kilobit per second, and we're modulating that onto the 1 gigahertz carrier, as we said previously. And all of the demo, including the notebook that you're seeing now, is running on the RF SoC. So it's the ARM A53s that's serving up what you're seeing at the moment in this notebook. We're going to execute some Python code to download the bit stream, which loads the RF SoC overlay onto the FPGA. We're then going to inspect the operation of the transmit signal chain, and we'll look at the output of this pulse shaping block. For those of you who are familiar with this, this is a root raised cosine transform we're doing here. And we're going to see 2 results. We're going to see the result of introspecting this in the time domain, but also in the frequency domain. And the frequency domain representation is actually accelerated on the FPGA using an IP block specifically for that purpose. So these are the characteristic in-phase and quadrature time domain signals that we expect to see. This is the corresponding frequency domain signal. And we can update this signal live from the FPGA, from the infrastructure that we have created. So that's the receive side. Switching now to the, that was the transmit side. Switching now to the receiver side, we're going to look at the fully demodulated symbols at the output of the whole signal chain. And here what we're going to do is we're going to execute some more Python code to grab some demodulated signals for us. And we're going to see two views. Again, the time domain view, but this time also a constellation map, which is very familiar to radio engineers. So in this case, we get the quadrature and in-phase symbols as we expect, and we can introspect those at various points. But we also get the constellation diagram. Now, these are the four symbols that are characteristic of QPSK, and the distance between them is a measure of the goodness of the system. The bigger the distance, the better in general. So we're going to create a new window for this for the moment because we want to rearrange the screen a little bit. So I'm going to create this second window, which I'll put over here, and tidy it up a little bit so that you get a good vision of that. And I'll fold down this one. And now I'm going to go to the RF block, and we're going to launch some Python code that will give us a widget which allows us to adjust the power level on the output of the transmit phase. So now if we reduce the power level, we see an immediate impact. Well, I would see an immediate impact if I was running the constellation diagram. Let me do that for you again. So you see that reducing the power level has the effect of changing the position of the symbols on the map. Now, the further apart they are, the better. So as you would expect, as we reduce the power transmitter output, we see a degradation in the ISI capability. So this is, there's more to show, but this is a short demo, so I'll conclude at this point. What we've done is shown you the application of open source data science tools to RF SOC, and we think this is a huge future opportunity for us.
So some of the wins here are that we take the C++ APIs for RF SOC, we wrap them in Python, so now we can script whatever environment we want. We want to visualize things, so we're taking data back from the array. We're using some of the ND array, some of the NumPy techniques to get those arrays back in. And then we're using open source data science visualization tools. This is Plotly extended. So to data scientists, they use this all the time. To us, it seems like a gift that we can suddenly couple this up into embedded systems and start to build prototypes and visualize and see what's going on. So we're continuing to explore this. We've done some other notebooks. This and
the context for this demo.
This and this other notebook. These other notebooks are available. So if you have an RF SOC board, you can download this software. You can re-image your SD card, and exactly the demo that you've seen will be available to you to run and experiment with. There's also one that programs up the forward error correction blocks, the SD, the soft decision forward error correction blocks, under different modulation schemes, and shows you the bit error rates according to SNR under different conditions. So we think this is a really good way to let people have access to fairly complex technology, explain how it works, demonstrate new technologies, etc., and very scalable and very consistent. And we like a lot that it's not something we invented, but rather we're repurposing the awesome work that's come out of the Jupyter community. And they continue to innovate, and we continue to get benefits from that. So, for example, if you know Jupyter, you know that anything I showed you in the notebook, I can create, by a couple of clicks, a slideshow of automatically within Jupyter. So you could even do your presentation based on the notebook. We also run this now on the Alveo cards. So this is an example of a Jupyter notebook layered on top of the OpenCL stuff that you saw earlier, running on an Alveo card, allowing us to do the same type of thing. And here again, part of the attraction is a good Python interface can abstract a lot of the technical details of some of these C++ interfaces that are just a little bit overwhelming when the focus of your task is not that, but something else. We see an opportunity going forward, and this is a question that I'm going to pose to you, and hopefully some of you are more advanced in this than I am and can guide us. But if you want to do Jupyter at scale, you know, so every semester or every year, the data science course at Berkeley teaches, I think it's 1,800 students data science, and they use Jupyter for that. So what they use is Jupyter Hub, and Jupyter Hub essentially has three parts: this reverse proxy, the authenticator, and the spawner. So a student logs in, and they effectively get a Docker instance created for them. And that Docker instance then has the Jupyter Notebook environment that they do for their data science. And they also have automated some of the assessment material as well, and various other things. But we looked at this and thought, that's pretty cool. But what we were wondering was, and here we got a bit lucky, because we were thinking of using this at scale, and then we noticed that some of the guys at NERSC are actually doing this independently of us and are ahead of us. So this is the National Energy Research Supercomputing Groups. Again, there's one at Livermore Lab, the Berkeley Livermore Lab. And here they have these supercomputers, this Cori thing, and they have a new class of users, not the traditional HPC guys, but these data scientists. And data scientists spend a lot of time exploring the data. They're not actually sure what it is that they're necessarily looking for. And I think there's a parallel here with radio science, or radio astronomy. Sometimes you're looking at the data wondering, is this real? Did I make the right measurement? Is there something valuable in here or not? And you have to go backwards and forwards before you can build your thesis, if you like. And so they're finding this community is reaching out to them and saying, we need to be able to take a Python program and scale it up to 500 nodes, but HPC is a hostile environment for them. And this is a quote from the Paderborn in Germany, the chap managing the supercomputer center there at the University of Paderborn, said for a lot of data scientists, this is a hostile environment. So the guys at NERSC have come up with the idea of front-ending this with Jupyter Hub. And they're now using Jupyter Hub so that from my notebook on my PC, I can have access to the HPC facility, and I can spawn off 200 or 300 nodes at the same time with PYNQ. And we think this is a very interesting development. So we looked at this and we thought, this is, and by the way, the components of Jupyter Hub that are meant to be user configurable. So if your authentication system isn't the one that they ship, if it's LDAP or something else, you can just plug in the different authentication systems. So it's very configurable. If you don't want to use Docker or Kubernetes, or you want to use something else as a backend, that's configurable. And this isn't one instance. There's a workshop that was held at Berkeley last month, and there were about 9 different HPC centers exploring this approach. So that gave me a lot of enthusiasm, if you will, that this might have legs. And what I was imagining was this might be a way to control a number of RSOC boards, for example, or a number of Alveo boards in a data center beside RSOC boards, perhaps remotely at the measurement point, a way to scale it, a way to do workshops on these platforms, etc. So I'd be interested in a discussion with anybody who's interested in this idea. But more than anything else, I think leveraging the outstanding work that's already going on, this is all open source work, of course. So, for example, just one thing these guys have done is Slurm is one of the workload managers that's used a lot in HPC. So there's now a Jupyter Lab extension for Slurm. So you can actually be in your notebook and manage your workload and see what the status is and restart machines that have, bottlenecked or whatever. And of course, they're also handling the problem, because they're an HPC core, of how do we handle the large data sets. And they have, data sets almost as large as yours. You can imagine Los Alamos nuclear simulations and various other things. So I think they have many of the common ingredients. And I was imagining, if you will, an array of RSOC cards somewhere near an antenna with a cluster of Alveo cards in some machines here, and the whole thing being accessible across the campus anywhere, just from somebody with the Jupyter Notebook, the right authentication, and the ability to dial in and see how the system is going or gather data, etc. So that's the end of the PYNQ part. I'll pause for breath and any questions. It uses all standard Xilinx parts. Okay. So currently, let me say, first of all, let me answer for the original PYNQ on Zinc devices. So that's the ARM processors and the FPGA. We reconfigure the FPGA in its entirety. Okay, so every time we bring in a new notebook or load another overlay, it comes down in its entirety. That's the majority of our examples. Now, we actually have examples of dynamically updating those overlays during runtime. So we're actually partnering with some guys at BYU who made some changes to the Linux device tree, such that we can change the hardware, and the hard part then is to get the software to reflect the changes in the hardware, and the device tree can be updated at runtime to reflect the new hardware. So we have done work like that. So that's on the Zinc side. Now, if we go to the Alveo cards, I showed you earlier on that for the PCIe to operate, there is the shell component, which must always be present on the FPGA. That's the PCIe endpoint, if you like. that design by default is dynamically reconfigurable. The bit streams that get loaded on in addition to the PCIe endpoint. But to some extent, that's almost you're almost oblivious to that. That's hidden by the infrastructure. So okay, in the interest of time. So we're entering a new world. It's clear that, and here if you do get the chance to read or listen to the very good talk by Hennessy and Patterson, the ACM Turing talk, about what's coming, they'll tell you Dennard and Moore are essentially at the end of their projected lives, and Amdahl's law is increasingly difficult to deliver with the kinds of modern processors that we have today. So highly cached systems, multi-core, etc. It's difficult to carve out the performance. And there are a whole pile of new and very complex applications coming down. One is that it seems that we have to do AI with everything. It doesn't matter what problem you're doing. I actually think that I'm waiting for the Casper AI workshop. It will come. I'll be the one to predict it. It will come. But I know, for example, the guys at the CERN with the Large Hadron Collider and with the with particle detectors, right up close to the particle detectors now, they're using AI to filter out objects of little interest. So you can imagine they get hit with all this data, and they're trying to find the nuggets in the data. So if they can filter that with AI, that's cool. So I would imagine you have something similar going on there. And the next thing is, and I think we saw some of that in the talks about GPUs, is it's no longer a MATLAB double precision floating point world. Even the GPU guys are 4 bits and lower. We see reduced precision. We see weights that can be even binary neural networks work, and thresholds, etc., that can be taken down. And then increasingly real-time low latency. Now, for example, 5G mobile just assumes this. It's assumed that we're going to be able to do low latency remote tasks. So the future should be surgery where the part moves as the surgeon moves, not 15 seconds later or whatever, because we have low latency networks enabled by things like 5G and IoT, etc. So these are not demands that can be typically solved by today's compute platforms. And Xilinx's response to this is ACAP, Adaptive Compute Acceleration Platform. Adaptive in the sense that there are so many things that you have to address that it has to be capable of adapting not only to the different applications, but also to the changes. I mean, literally today, your neural network algorithm is probably obsolete in 18 months. That's how fast some of that space is working. You also have to be very low latency because you can't send everything back to the cloud, so you need to do more stuff at the edge. You need to be real time. You need to be low power. And these are not things that GPUs and CPUs have been designed for. So you need to think again. And so ACAP is a family of members. Versal is the first of these that we introduce. Now, let me say up front, I didn't make all the slides, so there will be some slides that look like they came out of marketing. In fact, they all came out of marketing. So these are better than my pink slides. So the first two members of this family are the AI Core series and the Prime series, and they differ primarily in that the AI Core series has these new AI engines that we talked about a little bit in Luke's talk, and I'll go into that in a little bit more detail. And we see that there will be different mixes required for different markets, basically. And we have a portfolio of building blocks with which we can assemble these devices so we can actually tune them for different market segments. And we'll show you some of those building blocks and how they work. So this is the Versal architecture in a slide. And you see the familiar ARM processors, the scalar processor, the A72, which is 64-bit dual core, and the ARM Cortex-R5, which is a real-time processor. Very important in things like automotive, very important for security, very important for real-time guarantees and stuff like that. The adaptive engines actually is the PL. Okay, so not sure why it was called an adaptive engine, but it is the PL. The AI engines are the new block. The DSP engines are actually part of the PL, but there's been so much work done revamping them and extending them that it was worth pulling it out. And then you see the PCIe and the C6 for the cache coherency, multiple memory controller interfaces, onboard HBM in certain ones, 58 gig on most, going up to 112 gigabit per second, multi-rate Ethernet, and very, very high capacity built on these SerDes cores, and then a range of other everything from MIPI to CAN FD, for example, CAN flexible data. And then right at the end, you see planned for the future is an RF-SOC version of this. So what Luke said with all of this applied to it. So the scalar engines are familiar, except that they're more powerful than previously. And there's also in here a block which wasn't highlighted, this platform management controller. Now this is the device that's responsible for configuring the part, for security, for authentication. So if there's hashing or SHA or AES encryption going on in the bit stream, this is the part that will control that. And also for delivering bit streams for dynamic reconfiguration. And this part supports dynamic reconfiguration in a really interesting and exciting way, which I'll come to in just a moment. So in addition to the two ARM processors, there's this platform management controller. And that in itself is a very powerful subsystem, but really you only see the services that it gives you rather than programming. And the ARM subsystems, they're more powerful than the ones you've seen to date. The 1.7 gig is or 1. See, am I reading that correctly? Yeah. And this is a 2 by and then the 1.4 on the R5s, etc. And here, for example, you can do things like lockstep. You can have the two processors executing the same code so that if you get out of lockstep, you know you've got a problem, etc. So this is very targeted at security and that side of the house. This is the kind of thing that would do your Linux, your network interface for your low-speed interfacing, etc., and command and control, if you will. So the adaptable engines, then, essentially this is the fabric. Now the fabric has been considerably improved, and I'm not going to go into all of the details of that in the interest of time, but what we've done is we have a very valuable, we have a very strong value proposition in the fabric itself. Now, some of the problems we had with it, though, were congestion, how does it scale, etc., and how we've addressed some of those issues. And how it alleviates a lot of the congestion you would get if your ARM PL was just simply to scale, you know, linearly. So one of the key things is the memory hierarchy, and you see here from the distributed RAMs to the block RAMs. You've got the traditional block RAM at 36 kilobytes, and then the ultra RAMs at 288 kilobytes. There's a new accelerator RAM in some of the fabrics. Then you have HBM and external memory. Now, one of the key things about this 7-nanometer game, if you will, is that the transistors scale, but the wires don't scale. So that's one of your problems. The second problem is the biggest problem in compute today is not so much compute as getting the data to and from the compute. So all these level 2, level 3 caches and all these flushes and misses, I mean, they just really hurt you. And so having data that is close to the compute and having compute that can be right-sized along with the memories for the data, we think is a critical differentiating advantage. And that's what we have in the PL, and that's what we have in the other fabrics as well. So this ability to have this local memory at different levels and have the bandwidth to it is critical to the Versal thinking. The DSP engines and the AI engines are complementary, and in some parts, like the part that we're talking about here, the AI series that has both, there are some parts that only have the DSP engines. And typically what happens there is the DSP engines have, they're larger or there are more of them. They do overlap a little bit, but not exclusively. So now we've got a variety of fixed point and floating point capabilities, some new form factors, precisions influenced by HPC. And here's an indication of the relative performance in the different domains, if you will. This is the int8 dot product. This is complex 18 by 8, and this is 32-bit single precision. And in each case, we're comparing to the 16-nanometer part that we have today on the Versal part. And despite what I think Luke said, that there might be a compatibility problem, but in fact, you should be able to take most of your existing stuff onto this DSP 58, and it should work reasonably straightforward.
So what is the difference between the Versal DSP engines compared to the normal DSP 48 that is in the FPGA 5?
It's been quite intensively overhauled, so we refer to it now as DSP 58, for example, so it's wider. It's got a lot of new functions in there. You can do, it would be hard for me to remember them all actually, but you can do like expression matching up to like 118 bits and a whole variety of other things. So it's been extended dramatically, and it's like a superset of what you saw before. That's
Still in the FPGA fabric.
yes,
Not like software.
yes, yes. It's still in the FPGA fabric, and I apologize in advance. There are at least 3 or 4 subjects here where we could have a complete talk on, you know, very easily. The DSP engines would be one of them, but the other thing is, for some devices that don't have the AI engines, you might want to do some AI. So, for example, Int8 might be, you might use the DSPs for that under those circumstances. So you can trade things off.
Sorry, Patrick. Is it likely that those, the new DSP-58s might find their way into other families?
Good question. The honest answer is I don't know, but it makes sense to me. I guess it would be a marketing and, you know, financial decision as to I think people tend to go forward rather than, you know, backfill features is my experience. So I'd be skeptical, but I don't know, is the honest answer. So then we get to the AI engines, and this is an array of specialized new engines. You could, it's VLIW, SIMD, vector, fixed point and floating point processors. On the device which we're taping out first, which is the 1902, this is going to be, and I'm going to have to move it, this is going to be 400 of these tiles in the first device. So this is scalable. And you can use all of these tiles, some of these tiles, different combinations of these tiles, whatever you will. So you have here basically a scalar processor plus this vector processor, and then you have local memory with each of the tiles, and this is broken into 4 such that each tile can address its neighboring tiles memory also. So north, east, south, and west, you can dial into the memory map of your neighbor, and then if you want to do something a little less local, if you want to say connect or send data to let's say a tile at some distance from you, there's an interconnect that's exclusively associated with this for that purpose. A little bit more detail, I don't want to get too lost in this because there's a lot. This is a 32-bit RISC processor. It's got some nonlinear functions, like I think it's square root and a few other awkward things to compute. This is the vector unit with both fixed point and floating point. See, it's a 512 data path. It's a 128 instruction length. You see here parallel. These are address generation units. So multiple address generation units allow you to do multiple operands simultaneously. So you can set up this guy to pull the data from here, this guy to pull it from there, and then the result is going somewhere else. So in total, if you include streaming along with computation, you can actually do 7 tasks in parallel. So you can have 7 wide parallelism in here. And again, you see that a range of data paths a range of precisions, etc., that are supported. So very high performance, very high bandwidth between them, and all programmed in C, C++. Okay, so these are not like an FPGA in that sense. You program these in C, C++, and then you can get to higher levels where we give you essentially an overlay. Let's say somebody designed something for using one of these with a particular convolutional neural network. That overlay, we can then configure just the neural network you want, and effectively that would tailor the overlay to so these framework ideas are coming in here as well. I wasn't aware this was animated. Oh, I didn't know that was there. So obviously I looked at this slide but didn't play that one before. So this is the network on chip. These are mid-range part. This is a 1 gig network. It's 128 bits wide. There's a kind of vertical component to it and a horizontal component, so VNOC, HNOC. The VNOC is, let me just get this right, the VNOC is maximum of 2 channels, the horizontal NOC is maximum 4. That gives you 64 gigabytes per second bandwidth in the horizontal NOC, just that. And the processors actually access a DRAM through the NOC. The fabric is broken into sub-fabric regions, each one of which is an independent clocking region and a standalone in its own right. Each one of those regions has an ingress and an egress port onto the NOC. So every part of the FPGA has a region that has one in, one out port. And they can, for example, if you wanted to, you could take data from this end and use the NOT to drop it into the other end of the FPGA. You can also reconfigure those regions using the platform management controller. So you can actually load new functions dynamically. And so very, very powerful capabilities. And you can set up different quality of service, so you can have low latency. ISOC is kind of a bounded latency, and you can also have best effort, etc. And it comes with a NOC compiler, so you give it essentially the performance you want, the constraints you have, and it compiles the solution for you. I took this slide out and then put it back in again because Luke said I would talk about the SerDes. I think these were well covered in the networking talk earlier today. But Xilinx has market leadership in SerDes for many years, and these represent incredible state-of-the-art transceivers to have, and there are many of these available on the different parts. So we typically are known for our SerDes leadership. Obviously, 100 gig is not commonplace in embedded type parts today, but it'll come. And these are also things that we need for data center today anyway. The integrated shell concept, and I'm almost done, so let me just see. Sorry. Okay, let me do that. The essence of this is that this part boots up without any bit streams. Okay, so it boots in milliseconds. The processors are up, the networks are up, the CCIX is up, the PCIe is up. So you don't have to have a soft shell here. We showed you that at the start with the Alveo cards. That goes away. The system is talking to the PCIe and the CCIX is up, and it's all ready to go. You can load the bit stream before that if you want to. You can load the bit stream after that if you want to. But this is a system that basically powers on, ready to talk to the world that it's connected to. In terms of software, we have the traditional tools. We have the embedded tools. All right.